Okay, we've got 1:30. Why don't we get started? Good afternoon, research methods. Welcome to Wednesday of week number 13. This will be our last session before our section exam, and then we're off to Thanksgiving break. Who's ready for Thanksgiving break? Yay, all right, we're almost there. It's a little bit more, and so we'll spend most of today preparing based on the questions that you have, actually the teaching that you'll be doing across the PowerPoints that we've had since our last section exam. And just to remind you, this is what we've got available on the S drive and also available on Blackboard. A little bit of background on how many points this thing is worth and what the emphasis will be on. As we've said many times, the emphasis will be on the material since October 28th. We have maybe 7 or 8 different PowerPoints, the corresponding items along the way. There was a homework analysis, article analysis, a homework set or 2 along the way. Lots of videos along the way, so hopefully we'll pull all of that together. One of the things that we might have you do, we might have you read a brief article or a abstract and make some sense out of it. We might hand you some Spss output and not ask you to do a lot of computation on it, but just to make some sense out of the output. So you wouldn't have to do the Spss problem directly. You would have to do that on a computer test in some future week. But for this coming Friday, we might hand you some Spss and say, okay, based on this, what kinds of conclusions can you draw and so forth. So to get ourselves warmed up with that, what I thought we might do is just a couple of quick items inside of Spss so we can generate some output, do some interpretation, and then we'll jump right into the teaching items that we asked you to think about for today, for the different PowerPoints that we've had since October 28th. So could you all please open up Spss, and while that's coming up, we'll just remind you of what we did yesterday. We were learning about Factorial Anova, and we made a really long computation. It took most of the session yesterday to get to this F table. So we'll just open up a blank Spss, and we'll have Spss do in just a couple of clicks what it took most of yesterday to do manually inside of Excel. As you might remember, we were doing a 3x3. Factor A had 3 levels, factor B had 3 levels, and we were able to come to these findings where we actually wound up with a statistically significant effect for each of the 3 factors of interest: factor A, factor B, and factor A by B. Okay, by a show of hands, how many people have a blank Spss up? Okay, all right. So what we'll do is, in just a moment, we'll go into Excel. You don't need to be in Excel yet, and we'll copy and paste some data from here into Spss, and then we'll see how we would get Spss to do what we did yesterday. Okay. All right, so just to remind you of what some of the ideas were here, we had a 3x3, and the data set itself I have inside of Excel, and we had some scores, our dependent variable. We had factor A, and people were either in level 1 or 2 or 3, and we had factor B, and people were either in level 1 or 2 or 3. And so we'll copy and paste those data in just a moment. What we do need to do, though, first, inside of Spss, is we need to set up our variables inside of variable view. And the 3 variables that we're going to be copying and pasting are going to be scores, factor A, and factor B. Okay? We typically have one other variable that we start out with in our blank sheet. So this is probably what you have there. Can we all yell out, what do we typically put in as our first variable? Participant? Okay, why don't we do that? If you'll join me in variable view, we'll put in the word participant. Something else that we do with this? Okay, we turn it into a string. What does that buy us? Why do we do that? I think I hear it. But we can put in letters, right? So we can put in participant 1 or P1, P2, P3, and all of that. Okay. So we've got a blank blank Spss sheet, and now we have our first participant. And just taking a peek at how the variables were organized inside of what we're going to cut and paste in Excel, we had scores, which would be this scale variable. Okay. And then we have this categorical variable of factor A and factor B. We learned the other day that we can use this abstract coding. We can say first level of factor A, second level of factor A, third level, and so forth. So why don't we go over to Spss one more time, and we'll put in these 3 variables inside of variable view. We'll go to here, and we'll put in scores. Okay. And we can change the measure type for scores to be scale. Okay. And then we're going to make factor A a variable that is nominal. We'll make factor B a variable that is nominal. You might remember that we had seen an example in PowerPoint where we were giving different kinds of feedback. We were giving either praise or criticism or silence, and then we can have different levels of complexity in the puzzles that people were solving. They can be complex, they can be simple. We can add an intermediate level there too. So we might make all of those variables nominal. Okay? Who's got that much? Is that working? Okay. And people are following this structure, following what's going on here. So if we flip over just for a moment to data view, you'll see that what we used to have going on in rows in our variable view have now turned into columns in our data view, and we could put in something like the 45 different participants that we had. You might remember that yesterday we had 5 participants in each of 9 conditions. We had a 3 by 3, so that's where the 9 conditions came from. So we had 9 conditions with 5 people each, 45 different participants. We won't waste our time today by putting in P1, P2, P3, but we could do that, right? And just to make sure that it's working, can we do a couple of those? Can we just do P1 and P2, and we can see that it in fact is taking in our strings, our letters. I think somebody the other day hadn't clicked on string and they were putting in P2 but nothing was coming up there. How many people are getting that much? They're able to enter that? Okay, really good. All right, so let's do it this way then. If we can minimize this just for a second, and if we can go over to where we were yesterday, if you'll dial out to the S drive and into our practice sets. Inside of the practice sets, we had some factorial exercises. Inside of the practice problems. And those were listed in something called the two-way between subject ANOVAs. So we'll let you dial out there. Once you go in there, there are 2 different Excel files. Okay. And we want the one that says factorial between subject exercises. So I'll let you catch up there. And when you get that far and you open it up and it's really big on your screen, can you raise your hand so I can see where people are? Okay, it looks like most of us are there. All right, and so that should look more or less like this. Okay, and you might be, maybe it opened up to, I don't know, cell A1, wherever it opened up to. We want to go over quite a bit, maybe over to cell or column U, V, or W, and you'll see that we've got scores, factor A and factor B, listed at about row 10. How many people can see that? They're able to find that? Okay. We're not going to copy over the words scores, factor A, and factor B, but we will start in the 7, and we'll grab that first row, we'll dial all the way down, we'll get this really big rectangle filled with information. From 7, I'll dial all the way down to this 3. I'll hold down the Shift key and click on that, and I'll get this really big rectangle filled with our 45 participants. Each one has a score. Each one has a factor A place, somewhere in the 3 levels of factor A. Each one has a factor B place, somewhere in the 3 levels of factor B. Who's following that? That work for us? Okay. This is an entirely independent subject design. So we have any one person in just some combination of these 2, but they're not getting more than any one level of factor A, not getting more than any one level of factor B. So if we now do Control C, okay, and we get that ring around the rosy, how many people are getting that? Okay, really good. And then if we click back over to where we were just a moment ago inside of SPSS, and we can click now on scores. Okay. We'll click on scores, and we'll do a Control V for victory. It takes just a moment, and if you dial down, you'll see that you should now have 45 rows filled with information just at one click, or one flick of the hand with Control V. And there we are. And you can see that the only numbers we get in factor A and factor B are either a 1, 2, or a 3, versus all these different kinds of scores that we get here for our score variable. How many people have that? Anybody get lost? Okay. All right. So what we're going to do now is to see if we can do in a few clicks what it took all of yesterday to accomplish, and we'll see if we can get a factorial ANOVA going. Anybody want to remind us how we might get started here? Analyze. Okay, really good. We've done it once or twice before, but we haven't done it recently. Anybody have an idea? We are going to be comparing means, but counterintuitively, we're not going to click on compare means. General linear model, not generalized linear model, very confusingly. And this time we're going to go with the univariate type. Okay, so we went general linear model, univariate. I'll let you click that. Yes, please. Why are we going univariate? Very, very good question. And the question is especially good because the word univariate implies one variable, and we actually have 2 independent variables. Here, univariate is referring to the fact that we have only one dependent variable. if you take the next course up, Psych 370, we do some multivariate statistics where you might have either one or many independent variables and also many dependent variables. But this actually is still considered univariate because we have only one dv. Please, Jenna.
I'm just trying to remember, in which exercise do we use repeated measures?
Really good, okay? So we'll use repeated measures whenever our design contains at least one IV that is administered in a within-subject manner, or repeated measures. That's right. So for within a repeated measures are synonyms. Yeah, okay? This is entirely between. Each of those persons was either in one level and not the others of A. Same thing for B. So really good question. Yeah? Yeah, it's easy to get lost in these because a lot of similarities and we need to understand the design very carefully. So general linear model, and we're going to go univariate. And when you do that, you probably get something like this. Who's got that submenu? Did I lose anybody? Okay, really good. What's our dependent variable out of this list of variables? Scores. Why don't we slide that over? Okay. Some idea about what our independent variables might be. Factor A and factor B. And we put these, a little bit confusingly, into fixed factors. Just a brief note about that. Fixed factors means that we have set levels of factor A and set levels of factor B. We have level 1, 2, and 3. You can imagine you could have had a different variable, like maybe height or something, that would have been continuous. I'm 5'7", somebody else in the room might be 5'6", somebody else in the room might be 5'11", and we don't necessarily have fixed levels. But here we do have fixed levels, level 1, 2, or 3 in factor A, level 1, 2, or 3 in factor B. Is that okay? People following that? So actually for the rest of this semester we're going to be using fixed factors, not random factors. Okay? All right, let's do a couple of other things. Why don't we go into our options box, okay? And just to make sure everybody's there, who has the options box open? Okay, is that working for us? Good. Okay, we can click on all of these. If you can highlight all of them, I held down the shift key and I clicked on the bottom one. We can get means for all of those if we wanted to. We slide that over, and that's a good thing to see. Sometimes when we're reporting in APA style, we like to offer the means for all of that. We also like to get descriptive statistics. We might want to be able to report standard errors, standard deviations, something along these lines. Estimates of effect size. Can somebody tell us what the name of that might be when that comes out? It could have been Cohen's d. It's actually going to turn out to be partial or eta squared. Okay, eta squared is what is going to be there. Observed power. Who remembers hearing about that from the other day? Okay, and why don't we do one more? Over on this side, can we take homogeneity tests? And what's that going to be called? Levine, okay, right? It's going to tell us whether we have equal variance. So we took these first three and that one, and that's going to give us a whole lot of output. Okay? Who's got that? Work for us? Okay. We'll say continue, and there's one more thing we want to do. Post-Hoc tests. Why don't we click on Post-Hocs for factor A and for factor B? And we can do a few of these. Why don't we just click on Chef-A in the interest of time? We'll do just one post-hoc test. The Chef-A is a relatively conservative correction for cumulative type 1 error. It will help us pinpoint where any differences might be that we would find in factor A all by itself or in factor B all by itself. Okay? So we clicked on Chef-A. Who's okay with that? All right, now this will take just a little bit of time. If we click on OK, you might go into a slight pause, and then you'll get a lot of information here. We're getting all the means for factor A crossed with these different levels of factor B. Okay, those are the means. And we'll let somebody here help us out with the interpretation of what we should do now. So we've clicked on everything. We've got some SPSS output. Just pretend that on Friday I handed you this output. Okay? And you knew that it was a completely independent subjects design, completely between subjects design. What would a good first step be? Okay, we'll go with Meg. Is that a hand or you're not so sure? It's okay if you're not sure. Okay, that's all right. I think I saw a hand in the back or two. We'll go with Kip and then with Jenna. Okay. Right. Okay. So we have in any one of these cells, we have a mean and we have some dispersion that we might describe by standard deviation. And what Levine is telling us is the dispersions are pretty similar to each other. They're not going to be exactly the same, but they're sufficiently similar that we can say we have a satisfied equal variance assumption. Who's okay with that? Okay. Now here's the next bit. Why don't we drop on down? And we'll see if anybody can help us interpret this one, the test of between subject effects. It's a little bit busy. You might have seen output like this in the readings for yesterday, or the readings, yeah, it was the readings for yesterday in our SPSS guidebook. Anybody want to help us out with this, the interpretation of this busy box? It's actually a lot busier than it needs to be. I wish they didn't give us corrected model. or intercept. We actually don't need those first two lines. What we do want to see is the information that we're typically used to seeing, the sums of squares, degrees of freedom, and the f value and all of that for factor A, factor B, and factor A by B. Who's able to pull that out of the center of that box? Can you see that there? Okay. All right. If you'll stay right where you are, I'm just going to flip up what we did yesterday. We did this, same sheet that we just copied from, and we came to this stuff. Okay. Can anybody corroborate these numbers on your SPSS output? And people are able to see that, okay? So SPSS got it right? 4.68, is that roughly what you have within rounding? Okay. And then for factor B, the F value is 5.643 within rounding, and 5.9108 and some change within rounding. Yeah, okay. All right, and then we've got these sig values, 0.0156, 007, and 0009. That working for us? Okay, really good. The eta squareds, they actually call these partial eta squareds for reasons that we can get into after the exam, but we won't need to do that for the exam. Roughly 20%, 23, and 39% of the variation explained. And people can corroborate those numbers. Anybody not finding those in the SPSS output? Okay? All right, so all of that should be confirming for you that we can go through all these steps with basic ratios and squared AB matrices and so forth, and it is confirmed inside of SPSS that we get exactly those same numbers. Okay? All right. All right. One last bit, just in case this comes up on the test, because this could be a fair question for the test. We're looking at the output one more time, and if you'll slide with me just over to the far right-hand side of the same box, okay? Somebody want to help us with the interpretation of power? So again, in the center of that box, we have factor A, factor B, and factor A by B. Can somebody help us out with that interpretation? Okay, thanks. Katie.
Well, I think that's the statistical power, so there's a pretty high chance of us finding an effect between variables if there's one.
That's right, okay. And it turns out that in this case, everything was significant, but it didn't have to be. And had we come up non-significant, it would be really helpful for us to report to our reader, yes, we were non-significant, and this was our level of power. Basically tells the reader how good our fishing net was from the other day. Okay, that's the indication of, just as Katie said, the probability of finding an effect if an effect is there. Okay, maybe we'll do one more thing. Can somebody help us out with this? This could be part of your, maybe part of your handout for Friday. I could hand you something like this. I wouldn't ask you to compute it. Okay, I might ask you to compute this in a few weeks if we're doing a computer exam, but I might hand you something like this and see if you can make some sense out of this Shefay box. Anybody want to help us out with that? So I'm down under factor A for the moment. Anybody want to help us out with what's going on in this Shefay box? People are not sure. Okay, good. All right, really good. We've actually done this twice, but not in about 10 days. So we'll go back to this. So first, who remembers the name Shefay? Okay, who remembers clicking on Post-Hoc Tests a moment ago? That worked for, okay, really good. So Shefay is one of the Post-Hoc Tests. We use Post-Hoc Tests to help pinpoint where we might have a difference from our song from Sesame Street. One of these things is not like the others. We saw that factor A is significant. How many levels were there in factor A? Can we all yell it out? 3 levels? Okay, so when there's a difference, and the Anova tells us there's a difference, it doesn't tell us where that difference is. Who's okay with that? Okay? The Shefay test, because it's a post-hoc test, will help us pinpoint that. So we can take factor A level 1 and compare it to factor A level 2, and then we can see if that turns out to be a significant difference or not. And it turns out that that actually is a significant difference because it's at 0.017. Who's following that logic? Did I lose anybody on that? Yeah, certainly. Okay, so the big picture here, Meg, is the idea that first in the Anova, we had 3 levels of factor A. So far, so good. The Anova also told us yesterday and today that if we looked at factor A, okay, here's factor A. If we took a look at that, it turns out that we have a significant factor A. So far, so good? So that tells us that at least one of the levels is not like the others. Okay, we have a difference there somewhere. It doesn't tell us, though, where it is. And the same thing for factor B. Just while we're here, it turns out factor B is also significant, but it doesn't tell us where that is. So we use post-hoc tests to do 2 things for us. This is a good review because there's a good chance there's going to be some related question like this on Friday. And that is the post-hoc tests help us pinpoint where that difference actually is, okay? Basically by doing t-tests. I'll call this back up again. Basically, they're running t-tests here. And not only are they helping us understand where the differences are, but they're also making a correction for cumulative type 1 error. And in this case, it's a Chaffee correction, a relatively conservative correction. Okay? So we compared factor A level 1 to factor A level 2. We got a difference of 2.2667, and that turned out to be a statistically significant difference at the 0.017 alpha level. Does that help? Okay? And then within that same box, we can compare level 1 to level 3. Okay? And that one turned out to be non-significant after Chaffee correction. And then you get all the pairwise comparisons. You can focus on level 2 and compare it to 1 and 3. Lastly, you can focus on level 3, compare it to levels 1 and 2. And there's some redundancy here. You'll get some of the same numbers a few times because we're either doing 2 and 1 or 1 and 2 kind of a thing. Right? Who's okay with that? Who's lost by that? Anybody still okay? You're still okay? So Brittany's not entirely sure. Why don't we do it this way, Brittany? Why don't we do the same kind of logic exactly? We'll just pick out on factor B. Okay? So here's factor B if we dial down. Okay? And now we're looking at factor B's output. And we know from earlier in our SPSS output that factor B is statistically significant. Let me check in with you, Brittany, and make sure that's okay. Factor B was sig. Okay? Now what we don't know is which of those levels is different from the others. Okay? And what this does is it sets up all the pairwise comparisons, level 1 versus 2, 1 versus 3, and so on down the line. And all we have to do is take a look at the particular pairing, maybe 1 versus 2. We'll go over to a sig value, and we'll see that we've got, in this case, statistical significance when we compare 1 to 2. And interestingly here, when we compare 1 to 3, that was also different. Does that work? Okay, right? But if we compare, let's see, level 2 to level 3, it turns out to be non-significantly different. So it looks like in this particular factor, factor B, 1 was the one that was quite different from the other two. Levels 2 and 3 were quite similar to each other. At least they were statistically indistinguishable. We'll put it that way. Please go ahead, Jenner.
So the answer would be that 1 and 2, or the comparison between 1 and 2 is significant, as is 1 and 3, as is 2 and 1, and 3 and 1. And that would be your answer?
Yeah, that actually might be more than what we needed, because when you told me that 1 and 2 were different from each other, you implied that 2 and 1 were different from each other. Okay. So this box contains plenty of redundancy, but what you said was actually correct. So what the post-hocs help us do is find out where that difference actually was. Okay? So we've seen that a few times, but it's always a busy box and it's always worth repeating. All right, who's okay with all of that? Questions about any of that output? For Friday, you will not have to generate this. I bet you could, but you won't have to do that. For some other Friday, after we come back, we'll go over this again, and we'll give you practice clicking within our, but we might hand you something like this and say, okay, how do we do, I won't say in so many words, how do we do on Levine? I might say something like, how do we do on the assumptions, or evaluate this, that kind of a thing. Please go ahead, Rachel.
And this is a factorial Nova?
It is.
Okay, and why do we use the factorial Nova versus the two-way, other one?
The one way.
Yeah.
Yeah, okay. So good question. It's a good orienting question. And actually, this might help us begin to transition into the PowerPoints. We'll have people teach me. Well, I'll leave this up just in case there are other questions. But factorial only means we have more than one independent variable. Here we have factor A and we have factor B. Those are the two factors that we have. Before we got to this week and last week, we only worked our way up to having one independent variable. Okay? And we started out, as you might remember, by going back to your independent samples and Anova slides. I think that might have been October 28th or thereabouts. We started out learning about Anova. Anova was new because we had more than two levels of a variable. We did t-tests where we can compare two means to each other. Then we got to this Anova thing. It allows us to compare many, many levels within one variable. We did that between subjects. The following week, we did that within subjects. And when we went within subjects, we had to now remove consistent individual differences, so we got that basic ratio S. But we could do many, many levels within one variable, between subjects, many, many levels within one variable, repeated measures. And then in the last 10 days or so, we've been working on this factorial bit. And that's when we start getting factor A, factor B, and the interactions. Mm-hmm. All of this is still univariate because we have only one dependent variable at a time. If you take an upper level stats course, we'll get you into multivariate statistics, but that's not this semester. By the way, just a simple example of that, if you wanted to have an interest in traffic safety, some psychologists are interested in that aspect of behavior, traffic safety, and you talk about maybe good drivers and bad drivers. Can you give out some ideas about what makes for a good driver, or what are some indicators of good drivers versus bad drivers? What are some everyday ideas? Okay, how frequently do you stay within the speed limit? You might operationalize that by how frequently do you get traffic tickets or speeding tickets. Okay, that would be one index. Some other index that we could have? Sorry?
Patience.
Patience?
Yeah, patience level.
Okay, all right. So if we had some indicator of patience, we might say that good drivers are more patient than bad drivers. Okay, so one measure is patience. One measure is speed tickets. Was there?
Oh yeah, how many times you've been in an accident?
Okay, how many accidents you've had? Okay, something along this. So those are three different dependent variables, and all of those roll up into this abstraction called good driver, bad driver. And then we need some way of tracing all of those different dependent variables, right? And we would need multivariate statistics to do that. This semester, we're handling only one dependent variable at a time, okay? And which is why we call this univariate. Okay, something else about this before I put it away and just ask you to teach me about the different PowerPoints that we had. Okay, I think people are pretty comfortable in pulling information off of this. Okay, I'll put that down for the moment. And I wonder if I might go to 1028. And this is, as I said a moment ago, is how we started in ANOVAs, where we have more than two conditions. We started out in a simple one way that was independent subjects or between subjects. Okay, and I wonder if we can do it like this, just to make things interesting. Here's my student random number generator. I wouldn't ask anybody to come to the board, but we asked everybody if they would think about two things that they could teach me from this bit. And we asked you to jot down a slide number or so. So why don't a slide number or two. So why don't I hold this down? We'll see if somebody wants to offer us a slide number within the 1028 PowerPoint. Somebody yell stop. Okay, there's Giselle. Okay, all right. So if we can let you dial into what you might have had, Giselle, for 1028, can you throw out a slide number that you could teach us about? Any slide, doesn't matter to me. Or if you don't have a slide number, you want to just go by a title, that's okay also.
This whole thing kind of confused me, so I didn't really understand.
Okay, the whole thing kind of confused you. Okay, why don't we try somebody else? Maybe somebody else can teach us something. We'll see if somebody can give us some bit. Try somebody else. Somebody stop me. Okay, Hannah, can you throw out a number and get us started on something?
Yeah, well, it's like the 22 to 24.
Good. Okay, so this is where you'd like to start us off?
Yeah.
Okay. A lot of red, a lot of green there. Can you teach me anything about this?
Yeah.
Okay, thank you.
Well, basically just how you can tell the F ratio with a pie chart.
Okay,
So the F ratio is between, over, within.
excellent.
So when you're looking at that, you can see which one's bigger and which one's smaller to see whether the numerator or the denominator will be bigger.
Okay.
And that will tell you if it's greater than or less than 1.
Okay, right, and that's a wonderful start. So what happens if it's greater than 1? What might we infer? If we
Greater than 1, then you can reject.
we've got at least a chance at rejecting the null hypothesis, right? We'd probably have to run the stats, but nicely stated. And if it's less than 1, we've really got no chance at rejecting the null hypothesis. Okay, and that's going to be true. So you said that was 22 through 24 or something like that. We have a chance at rejecting HO here, no chance over here, and really no chance here as well. Okay, all right. That comes up in several different PowerPoints throughout this interval, or something like it. Sometimes we did it within subjects, sometimes we did it between subjects, sometimes we did it factorially, sometimes we did it with eta squared. That's actually a very good one to pick. Thank you, Hannah. Okay. I wonder if somebody else wants to offer one or two other slides from the 1028. I can use the random number generator, but maybe people wanted to call out one that they thought was particularly helpful to them, or that they found easy to explain or rewarding after they learned how to explain it. Okay, thanks, Brittany.
For me, it was starting with slide 14. I think it's the basic explanation of the Anova.
Okay.
So knowing that the Anova is the F statistic and
Synonymous? Yeah, right. Okay, good.
and so that, going off of what you were saying, it's the variability between groups divided by the variability within groups, and that things to note are things such as in the population, all means are equal.
Okay.
And then in the population, not all means are equal.
Okay.
And that for computation's sake.
Okay.
Knowing that this is where we started.
Very good.
That's what's helping me in this. That's what helped me.
Good, good. So we have a couple of hypotheses that we're going to test. Early on in the semester, we talked about how there are conditions that we have for hypotheses. They have to be testable. We can state them in fairly simple numbers. We can compare means, and we are doing a mean comparison here. And we're looking at the variability in scores that we might have between groups versus how fat the error bars are. That's what's going on in our denominator. So nicely stated. Okay, nice summary. Okay, something else from 1028. Yes, please. Katie's got something.
It helped me really understand what the F ratio was by where it's like the Anova unpacked.
Okay.
We did the treatment effects plus individual differences plus experimental error over individual differences plus experimental error.
Okay.
So, because when you just say variability between variability, then it's hard to really see what that.
Okay. Right. Yeah.
I can sort of get a better handle on what.
Really good, really good. Okay, so it helped to unpack this thing a bit. Okay, and you can see that the numerator and denominator both have a lot of similarity. They share experimental error. They share some individual differences. What's unique in the numerator is the treatment effects, right? So it might be the case that we have 0, 1, 2, and 3 milligrams of Prozac. Okay, that's what we're hoping is going to drive some change maybe in behavior as indexed by the Beck Depression Inventory. It might be that our treatment is doing nothing. Okay, and if our treatment is doing nothing, then we're going to wind up with a numerator pretty much similar to our denominator. We'll wind up with a ratio near 1, and that's not going to be significant. But if we get a really nice treatment effect, and that grows and grows and grows, our numerator is going to get bigger and bigger and bigger. The F ratio is going to get bigger. We're going to wind up way out in the tail of the F distribution, and we'll be able to say we've had a significant effect. It's unlikely to find that just by random chance. Okay, nicely done. Something else on 1028 before we move on to some other day. Maybe it helps. Yes, please go ahead.
I was a little confused on the equal variance assumption.
Good.
Is that the Levine?
That is, okay, so the Levine test is our indicator about whether we should retain the equal variance assumption or not. So those two do go together. Okay, anybody want to help us to understand intuitively what we mean by the equal variance assumption? We touched on it a few minutes ago, but maybe somebody can offer us an idea about that. Okay, thanks, Mira. Yeah. So that's actually the null hypothesis. Okay, so but that's a really good start. That's a really good start because we had something conceptually similar to that. Okay, somebody else want to build on that? Actually, Mira's given us a very good start. So this Levine thing, right? It's a test of homogeneity of variances. Let's see if we can develop just an intuition for what we mean by homogeneity of variance, also called equal variance. Anybody want to help us with that? What that's like? Yeah, thanks, Kate.
Well, I was actually kind of confused. I was going to ask this as well, but just in your PowerPoint, it just says for the Anova to be appropriate, the variance must be comparable across the groups or conditions.
Okay.
So, does that just mean that I actually have no idea what I mean?
Okay, so let's say that we have factor A, and this is A1. We'll call this A2. We'll make this small one here A3. We've got some kind of score over here. Okay, I'm going to leave something off of this. Can somebody help me complete this? If it were the case that the equal variance assumption were true, and that Levine had a value greater than 0.05 and we were to retain this, what might I add to this to make it such that this is still a true statement? Please go ahead, Jenny.
Measure of dispersion.
Okay.
Error bars.
Okay, so, okay, right. And do you have an idea, Jen, about how big those error bars might be relative to each other?
They would have to be roughly equal if you were going to.
Okay. Okay, so I'm going to freehand it, but I hope you'll see that just intuitively, that measure of dispersion, which is a variance of sorts, and that measure of dispersion and that measure of dispersion are about the same. The error bars are about equally sized. Who's okay with that? Okay. Suppose everything is the same, except we get something like a much greater level of dispersion in one of the conditions. I'll randomly pick this guy. We put a huge error bar in him, all the way up and all the way down. Okay. Really, really big error bar. Now we have a variance that big, a variance that big, and a variance that's really, really big. All of a sudden the variances are not equal to each other. They're very, very different. Who's okay with that? So all Levine is telling us is that these error bars the variance, which is, as you might remember, is relatable to standard deviation. Who remembers that mantra that related the standard deviation to the variance? The standard deviation is the square root of the variance. Okay? When they're very, very different from each other, then they're no longer equal, and we can't retain the equal variance assumption, and we have to reject it. And when that's true, Levine will tell us that the sig value here is less than 0.05. Okay?
So equal variances when the error bars are
roughly equal. Yeah, okay? Because the error bars show us about error variance or variability. Okay? Kip, please go ahead.
If the equal variance assumption is like turns out untrue,
Huh?
would you still continue with the test, or would you have to like stop there? Isn't that one of the underlying assumptions?
It is one of the underlying assumptions. If you, and in some SPSS output, there's one line if equal variance is assumed, there's a different line if it isn't assumed. Okay, so that would be one of the ways of doing it. In some SPSS output, they don't give you the alternate line, and then you probably just shouldn't use that test. You might just descriptively offer what the means were without drawing any kind of inference. It's a very good question. Okay, something else about this. 1028. Okay, why don't we keep on moving? We'll work our way on through. We'll see who wants to teach us something about, I'll put that one down. Our next one in sequence was 1029, and some of the big ideas there were F-tables and basic ratios. So after we've got the Anova out in front of you and we had some conversation about that, then we got to, gee, how do you go about pulling out that F-table? How do you fill it all up? And we introduced the basic ratios for the first time. So I wonder if we can now look at 1029, and we'll go to the student random number generator. We'll hold this down. Well, has somebody stopped me? Okay, there's a stop. Okay. Anything here, Katie, from 1029 you'd like to teach us about, or teach me about? I'll pretend I don't know. I can go to a different view if it helps. I can go to a slide sorter view, and maybe we can see more of them here.
I mean, a lot of this stuff is just like interpreting the table.
Okay. So can you teach me about that? Let's just go to any one of the tables, if that's all right. So let's just say we went here, okay? And I notice there's a question mark over there. Can you help me out with this? Okay.
Yeah, so for the p-value, you do f this.
Okay, right. FDIS would get me that p-value here. So normally we get the p-value in our F-table. We saw it in SPSS, and if we have a 2x2 design or a 3x3 design, we're going to get a p-value for each of our factors, factor A, factor B, and the A by B interaction. Okay? Okay, that helps. Okay. Something else. Anybody here want to help us on any of these? Maybe you want to teach us something, or something that you found helpful when you were preparing for how to teach me? We've got 32 slides here. Okay, yeah, thanks.
Well, I think just in general, a part that made it easy for me to break down the F-table was slides like 5 through 11.
Okay.
12.
5 through 12?
I saw the little questions below, like they're very simple questions, but broke it down.
Okay, right, yeah. So the F-table is actually a fair amount to look at all in one big swoop, but if you do it just one column at a time and you figure out what information is there, what information isn't there explicitly, but you can sort of pull it out. You can work your way back, for example, to how many groups there were, because we know something about how the degrees of freedom are computed, and so forth. And then other information, like maybe the validity of the study is not available, and you can't infer it in any way. Okay? All right? Very good. Yes, please.
Could you give us something like this on the test, where you give us tables with blanks and then...
Could be. Yeah, I haven't made up the test yet, but I think that would be a reasonable thing to think through. Please go ahead.
I just have a question. So on slide 31, I'm just kind of struggling with how to set these up. So why would you start with compare means? Why would you do compare means when we know that in this case, rather than what we just did?
Thank you, thank you. In SPSS, and so the one answer to this question, Jenna, is I can't tell you why the SPSS programmers lined up their menus the way that they did. But what I can tell you is that if you have only one variable, it's one independent variable, and it happens to be between subjects, then the easiest way to do that is by the one-way ANOVA under analyze compare means. Okay? You probably could pull it off under the univariate that we did a moment ago also, but there might be more boxes there than you would need, and it would be a little bit overwhelming for you. So I do like to start out with this one because the menu structure is simpler, but you probably could pull it off under the same menu that we used a moment ago, sliding in only one factor rather than two. Okay?
So I'm just trying to figure out like the difference between the independent, so for the independent samples, Anova, we still had one independent variable to so.
Okay, so what independent means is that you've got one group over here and another group over here. This group receives one level of the independent variable. This group receives a different level of the independent variable, and nobody receives both levels. Okay, so they're independent in that way. It's considered a one-way because we have only one independent variable. We can think of 0, 1, 2, and 3 milligrams. Okay, does that work for us? Okay. I could have played the game differently. I could have said, we're going to have a really, really long study, and we're going to take in all these depressed patients, and during the first week, you're going to be on 4 milligrams. During the second week, you're going to be on 2 milligrams, and I could randomize that. So everybody is eventually in all the conditions, but that would then be a repeated measures design. Okay. Great. Something else on this one? Yes, please.
I was just curious, are we going to have to be like getting an output, or are you just going to like give us an output?
I will not ask you to generate output on this time around. Okay. Now I might hand you some output or a fraction of the output and ask you to make some sense. Later on this semester, we'll do one more computer test where we'll have to go into SPSS and generate some stuff. We're going to keep it all conceptual for Friday. Okay. All right. Something else from 1029. All right. Why don't we put that one down? And we go on to the next one in sequence, which was now November 4th. And we're still in the domain of one-ways, but our big heading here is repeated measures designs. So this was somewhat related to Jenna's question a moment earlier. We still have just one independent variable, but we're playing the game differently. Every one of our participants now gets into all of the levels. I wonder, does somebody want to help us out with something they want to teach us on, or shall I go to the random number generator? How should we do that? Anybody have something they want to share with us they thought was a particularly helpful slide or one that they could teach us about? Here's the big view. I'll go to slide sorter so we can see a whole bunch of them. Some of the multicolored ones again. Okay, Jenna's got something.
Slide 5.
Okay.
Practice effects. So the issue within subjects or repeated measure design is that the participants may be doing better on something because they've been exposed to it
Okay.
more than once, or they might be doing worse because of like exhaustion.
Yeah, fatigue or maybe boredom. Yeah, okay.
So the way you can deal with that is by counterbalance.
Wonderful. Okay.
So I think that's with the complete and incomplete design. You can either have an incomplete design where each participant is exposed to each level one at one time, correct? Or you can do, and that's, I don't know, that's for between, and then you can do complete, which is where they get it more than once, but it's in a different order.
That's right. Okay, yeah, right. So it might be the case that for practical reasons, I've got condition A and I've got condition B. And I'm going to take half of you, and half of you will get A first, then B. The other half of you will get B first, then A. It's still entirely within subjects because everybody got A and everybody got B. Those are the two different levels of this one independent variable that we have. Okay? All right, so everybody got those two levels. But some of the people got level B first, some of the people got level A first. Okay? But everybody got each of those levels, and you got them only one time. So what we did was we did some counterbalancing, but we counterbalanced across the entire group. We weren't able to counterbalance within any one person. Who's following that? That work for us? That's incomplete, right? Now let's say I had a little more time, and maybe it didn't take me as long to administer any one level of this variable. I might be able to go something like A, B, B, A. So Catherine might be one of my participants, and I might put her in A, B, and then B, A. And so now we've counterbalanced even within Catherine. Not only has she gotten all the levels, but we've been able to balance even for each individual. We call that a complete counterbalancing. And the reason why you would choose one over the other is usually just a matter of practicality. This is usually the better counterbalancing, but for practical reasons, sometimes you just can't get there. So you counterbalance across people. Okay, that was a good one. Thank you for picking that one out. Something else in November 4th. Here are the 33 slides. Is that a hand, Madison, or just no? Okay, all right, that's fine. Okay, all right. Any questions about November 4th? Okay, thank you, Mira.
This is kind of a silly question, but for the AB,
Okay?
Is it the same as just doing like A, B, like why is this specific?
Okay, right. So let's see if we can do it this way. What's the difference between A, B, B, A, and A, B, excuse me, A, B, A, B? Okay, why is one of those maybe better than the other? I wonder if we can think of it this way, Mira. A, B, A, B. Okay? Here we have 1, 2, 3, 4 was our sequence. Does that work for us? Okay. If we added them up, 1 and 4 add up to 5, and 2 and 3 add up to 5, if you will. Does that work for you so far? Here, 1 and 3 add up to 4, 2 and 4 add up to 6. Okay, so the idea would be that these, the A's are always coming earlier. Right? The A's are always coming earlier than B's in this particular arrangement. And here, there are at least some cases where we've got this preceding that, and across the whole range, if you imagine that you're getting more and more tired, B is going to get zapped in this arrangement, A, B, because here you're more tired than you were here. Here you're more tired than you were here. So if there were a tremendous fatiguing going on, this would control for that in a way that this wouldn't. Does that work for you? If there's an improvement going on with every stroke we get a little bit better, then what would happen is B would be better positioned than A in this case, right? Because here, this B, you'll be more experienced than that A, and here, that one will be more experienced than that one. Here you've counterbalanced across that. Okay? Yeah, it's a subtle point, but thank you for asking about it. Okay, something else from 11.4. Okay, why don't we do it this way? We have a few minutes left, but not a lot, maybe 4 or 5 minutes left. Why don't we now just break it wide open to anything you want to teach about in 11.11, 11.12, or 11.18. Anything that you'd like to teach us about. Okay, so 3 different PowerPoints there, 3 different videos. There's probably an hour and a half worth of video there or something like that across those 3. Let you call out one of those dates. Okay, thank you.
In 11.12.
11.12, good.
When you talked about on slide 6, just how like the subtraction method
Okay,
and how we get that.
Okay.
Get this graph.
okay, right. So here we're talking about the subtraction method. Okay. Do you need a walkthrough on that, or you just found it helpful? Or okay, right, okay. And so can you just remind us, if we were to do the subtraction method, first, what would that buy us? Why would we bother doing the subtraction
Well,
method?
we're looking for an interaction
Okay.
between, well, if we do the levels of depression,
Right.
you could start with the non-depressed and then subtract down and then go on. And
Okay.
if, the numbers are very different.
Yeah.
Then there would be an interaction. If they aren't, there would not be.
Wonderful. If we have different differences, we have evidence for an interaction, right? And if we have a null hypothesis about the interaction, we would say really that we have same differences. So if we're differencing the accident type at each level, if we wound up with the same difference in each of those, we'd have no evidence for an interaction. Okay? When we get different differences, we can reject the null hypothesis about the interaction. Okay? Very good. Something else. Any of the remaining PowerPoints? Who's okay with everything? Yeah, we reject the null when we have different differences. Okay.
So you went over like 3 types of ANOVA.
Uh-huh.
Independent samples, within subjects, and the factorial.
Yeah.
Okay. And each ANOVA has only one independent variable but has different levels.
I'm only in 2 classes.
That's true of all of the ANOVAs, that they have at least one independent variable. What makes the difference between a one-way ANOVA and a factorial ANOVA is a one-way has one independent variable, hence the name one-way, and then a factorial ANOVA will have more than one. Okay? That's what that means. Yeah, sometimes people get a little confused about the difference between an independent variable and the levels of an independent variable. Right? Something else.
Sorry, the 3 types of ANOVA are independent.
One-way independent,
One-way independent,
one-way repeated measures,
two-way.
or factorial, of which 2-way is one example. It could be 3-way, it could be 4-way. We looked very briefly at a 3-way ANOVA. Okay. And those are described more or less on the very first slide in each of these cases. Like, well, if you pop into one of the PowerPoints, it will tell you which kind of ANOVA we're doing. You know, between subject, or which is also called independent samples, repeated measures, which is also called within subject, or factorial design, also called the complex design. Okay? All right. Something else? We have time for one last one. Okay, Mira's got one. The Bonferroni, okay?
Multiplying the sig value times the number of tests.
Excellent. Thank you for reminding us. Yes, Bonferroni, and that's done for within subject analyses, right? Because SPSS won't give us a Chaffee or a Tukey or something like that. So a very good point, Mira. Thank you. That we can use the Bonferroni to adjust for cumulative type 1 error. Okay? Very nicely done. Okay. Thank you all for your contributions today. Look forward to seeing you on Friday, and then we're off to Thanksgiving break. Hope you have a great day.
Wait, can you repeat, like, the number is the sig value times what?
Times what? Who can help us out with that?
It pushes back the sig value.
Yeah.
I know, but like sig value times.
There it was. I heard somebody say it. Number of t-tests.
Thank you.
You're welcome. Thank you. Have a great day.
Ice cream.
Yeah.
Thank you.
Okay. See you, Meg. Bye-bye, Maddie.